Let's go back, way back, to about 359 million years ago. The Devonian period has finally ended after 60 million years. This end is marked by the Hindenburg mass extinction event. There are plenty of theories about what caused it, including an asteroid strike, global cooling, volcanism, mercury poisoning, and a hole in the ozone layer. Of the 5 mass extinctions throughout Earth's history, Hindenburg was the least deadly. Still, America can thank this catastrophe for much of its present oil shale deposits. We are now at the beginning of the Carboniferous period. The average global temperature is about 10 degrees Fahrenheit warmer than in the 21st century, and sea levels are rising. The ice age that began at the entrance of the period has not yet made an impact. The oxygen-depleted air that marked the end of the Devonian is now up to about 20% and climbing. Insects are celebrating their 120 million year anniversary since their evolution from crustaceans, but they're not yet the destructive pests they soon will be. Amphibians are on the march. Fish have been trying to conquer dry land for quite a while, and they finally overcame the obstacles in the Devonian as newly evolved amphibians. By this time in the Carboniferous, they're well established. It's now the age of amphibians. But this is only the dull beginning of the action-packed Carboniferous. Moving forward 30 million years gives us a front row seat to geologic upheavals and genetic transformations that are only now beginning to unravel. Throughout the Carboniferous, the land masses were converging and mountain building and volcanoes were the results. By mid-period, the continents were on the verge of forming the supercontinent Pangaea, and because of these changing terraformations, the world was entering another glacial phase of the Karoo Ice Age. The Earth's average temperature dropped 14 degrees Fahrenheit from its high at the beginning of the period, and sea levels dropped precipitously. Shallow oceans dried, and the water world of the early Carboniferous was transformed into a narrow band of hot, lush jungles and humid swamps sandwiched between sheets of ice and snow. Animals and plants felt the squeeze for survival, and it was time for evolution to get creative. As oxygen continued to increase, so did insect bodies. Lack of predators may have been even more important for insect growth, but in any event, the largest insects on record began emerging at this time. It was during the Carboniferous that insects evolved into voracious herbivores that threatened the existence of the forests. In defense, plants developed thick lignin bark. The bark in those days, however, was many times thicker and more poisonous than the trees of the present. A waxy suberin polymer was also secreted by the flora that made the bark practically impossible for insects to penetrate. Not only couldn't insects digest the wood, but neither could the fungi and bacteria of that era. Plant evolution was a little quicker than their predators' lagging development. As a result, for tens of millions of years, unimaginable amounts of dead vegetation accumulated with little decay. These dead plants would eventually transform into the vast coal reserves of our age. By the end of the Carboniferous, saprophytic bacteria and fungi finally evolved enzymes to digest the lignin, which limited coal synthesis to just a relatively short geological time span. The cooling and drying of the mid-Carboniferous were especially stressful on amphibian survival. Even from early in the period, there were climatic upheavals, so it was never an easy life for semi-aquatic species. Some amphibians responded by laying eggs that resisted dehydration. It's no secret that amphibians, as do fish, lay eggs that seem better suited to sit on crackers. These eggs provide only minimal function and protection and need to incubate in water to prevent dehydration. Once hatched, a metamorphosis begins, and the offspring change from larva to tadpole to adult. Some present-day amphibians have evolved ways to lay eggs on land, and even to bypass larval and tadpole stages, allowing hatchlings to begin life as miniature adults. This strategy is an exceptional survival adaptation and not the overwhelming pattern. Sometime about 320 million years ago, a few amphibians began laying eggs that had tough, leathery shells that were filled with amniotic fluid. Biologists theorize that amniotic eggs may have emerged earlier in the Carboniferous, but there's no physical evidence yet. These gas-permeable shells were suited for the harsher, drier conditions of the land. The amniotic fluid would provide the nourishment the embryos needed to develop, not through staged metamorphosis, but with brain-augmenting thyroid hormone supplied by the fluid. The animals that now laid these leathery eggs and the hatchlings that broke out would henceforth be called amniots. Here come the amniots. Yet it's only part of the story, because the amniots were the ancestors of the reptiles and mammals. In other words, about 320 million years ago, the world proudly heralded the birth of two new classes of animals, the reptiles and the mammals. It was not as fast or neat as that, and there was quite a bit of evolving to do before the differences between the reptiles and mammals could even be recognized. The first step was taken, though, and that was the biggest. And that big step was when the egg increased its role and importance as the transport vehicle of incipient life. Despite an indistinguishable phenotype, these tetrapod amniots came in two varieties. One class was called Synapsida. This group had a single hole on each side of its skull behind the eye sockets. These extra holes are called temporal fenestra and designed to accommodate large, heavy jaw muscles. The other class was the Diapsida, also known as the Sauropsida. They evolved two additional holes on each side of their skulls for jaw muscles. A branch of the Synapsida would ultimately evolve into the mammals, while the Sauropsida would sire all the reptiles. The Carboniferous period ended approximately 299 million years ago, when the continents finally fused and the climate cooled even further, drying and withering the great swamps and rainforests. The Permian period had begun, and the age of amphibians began a long decline. Ironically, it was at the beginning of the Permian when the amphibians produced their most formidable champion, Archaeops, an 8-foot, 200-pound carnivore with teeth like a buzzsaw. Maybe it was their challenge to the amniots. In any case, Archaeops was no match against the thick-skinned, razor-toothed monsters the new classes had produced. The Permian period was a time when the Synapsida and Sauropsida diverged and started down their distinct evolutionary roads, although they still strongly resembled each other. It's true that fully recognized mammals and reptiles had not yet emerged, but because their differing destinies were already cast, it's completely understandable that each class gather its own team cheering section. By early Permian, the Synapsida had evolved into the Pelycosaurs, a formidable group of overachievers led by none other than Dimetrodon, the meanest, toughest, He-Man stuffest hombre that ever crossed the Rio Grande, and it was no mamby-pamby. From the Sauropsida emerged the Reptilia, relatively small, scurrying, lizard-like animals that spent their days trying to avoid the jaws of the Pelycosaurs. Although paleontologists loosely classify these ancient animals as reptiles, the class was considered proto-reptilian. It was not until about 265 million years ago that the common ancestor of all living reptiles emerged from the clade Sauria. After a reign of about 20 million years, Dimetrodon lost its crown and the Pelycosaurs transitioned into the Therapsids, many of which probably grew fur. They were no less menacing to the reptiles. While the reptiles remained small and nimble for most of the Permian, the proto-mammals grew large and powerful. Just before the Great Permian extinction, the Therapsids produced Gorgonopsia, a saber-toothed beast possibly the equal of Dimetrodon. Still within the Permian, a branch of the Therapsids evolved into the Cynodonts, the direct ancestors of the mammals. It seemed that the mammals were destined to inherit the earth. But then, just when everything was going our way, something happened. The Siberian traps erupted, and all the descendants of the Synapsids were eliminated, all but the relatively small, unassuming Cynodonts. The reptiles were not spared from the many extinctions and suffered devastating losses too. Most clades disappeared, mirroring the plight of the proto-mammals. Yet the reptiles had one stroke of good luck, and that was in the fact that of the few clades that survived, one of them was archosauriforms, the ancestral group that would become the dinosaurs. Fate had now been reversed, and it would take another 185 million years and another extinction event before the mammals would reclaim the title of Masters of the Earth. Thanks for watching. Talk to you soon.